As Michael said, my name's John. I work for a company called Swiftstack. I used to work for a company called Rackspace, and I live in San Francisco and flew all the way to the other side of the world to talk about Swift, and I'm happy to be here at my second LCA. So, what are we going to talk about today? I'm going to try to go very quickly because based on also some of the other conversations, I'm going to take a little detour and cover a couple of other things. But firstly, we are going to just talk about what is this use case. We talk about erasure codes and we talk about storage policies. What in the world are we doing this for? Let's talk about what the design is, how does it work, and then end with a demo. And that's going to be fun. But first, before we do all that kind of stuff, I need to start with a little bit of groundwork. By show of hands, how many people here know what Swift is? Okay. How many people here know conceptually at a high level how the design of Swift and the different components of Swift and how it's put together? Much less. That's why I have these slides in here. So that's great. So to start with, we need a couple of, we need to be speaking the same language. So let's start with a little bit of terminology. 4 things I want you to know right now is that what is a proxy? In Swift, we've got 2 major components of the system. The first is a proxy server, and the second is a storage node. The proxy server is responsible for coordinating all of the communication with the storage nodes and implements the majority of the Swift API. The proxy server is what a client, an end user, is actually talking to when they talk to a Swift cluster. You can have lots of proxy servers and load balance between them, and it's horizontally scalable. It's really great. When you have a storage node, the other part of Swift, there are 3 kinds of storage nodes, and they do, there's the account, the container, and the object, and they correspond to the 3 basic things that Swift talks about. An account keeps a listing of the containers inside of it and some aggregated metadata. Generally, when you have an account on a Swift cluster, or when you are given access to a Swift cluster, you are provisioned an account. You sign up for Rackspace Cloud Files, you're going to be given an endpoint, which is an account, and you can do whatever you want to inside of that account. It could be that your organization is deploying Swift and instead say your application has a particular Swift account and then, or maybe your department has a particular Swift account. But the point is, this is the high-level aggregation of where data is stored. Container stores the listing of the objects inside of it and has some aggregated metadata as well. And then the objects where the data is actually stored. So that's kind of where we go. Now, the way that's put together in the API is that it's a REST-based API so that you can use standard HTTP verbs and response codes to figure out what's going on and communicate with it. The first part of the API is just the domain. What am I talking to? You've got an API version, which has always been v1 for the past 4 years, and a very, very stable API. And then the 3 things you'll see there that correspond to the 3 different types of storage nodes are you've got the account, the container, and the object. And so you've got a flat namespace. You can't nest containers or anything like that, but object names can contain slashes. So are you with me so far? Great. OK, so we now know what a proxy server is. We know what the account is, the container, and the object. That's what we need to know to go forward. Now, the next thing I want to cover just very, very briefly is the data placement in Swift. I'm not going to go into a lot of detail here. You should have come to LCA last year, and you could have heard all about that. So if you didn't, sorry. To start with, here's an example, just copy and paste curl commands of an example put of an object into Swift. So the important point here is we're sending in an auth token. We've got my URL, which is my SAIO, port 8080, API version 1. And then we've got my account as auth_test, my container C, my object O, throw a couple bytes in there and put it down. This is the response you get. So that's really good. But what happens when you get actually down to the disk? So if you're going and looking on the disk, now this breaks the rule of every single slide presentation you've ever heard. So I'll just walk you through this little part here. Right in the middle here, you've got something that says ring locations. This is the, when you put something out on disk, it ends up being it's replicated throughout the cluster. So you've got an on-disk layout of how this actually works. This is going to come back into when we're talking about how storage policies are implemented and specifically with erasure codes. So in here, we've got an on-disk representation that basically involves the hash of the object name. And this is kind of important. So the other thing I want to point out here is that let's see, because I'm looking at I'm coming up to my detour here. When something's on disk, the point of Swift is to be able to abstract away this heterogeneous cluster of storage volumes. This is your hardware that is abstracted. And so this is what I want to take a slight detour on. I created these slides about 30 minutes ago after lunch based on the conversations we had before lunch. So here's what I wanted to talk about. Specifically wanted to address some of the things that were coming up about Swift pluggability and things like this. So I'll have hopefully some time for some questions at the end, and if we need to come back to this, we can. But the point is, as I said, for Swift, one of the fundamental design goals is the fact you've got a lot of data, billions of objects, you've got petabytes of data, and you need to be able to abstract away your actual storage hardware behind it. You do not want to tie together the thing you're storing on top of with the media that you're storing it upon. And the reason is because media fails, and number two, media changes over time. And specifically what you have is your client, and I pulled this from some presentations I gave several months ago. The point is the media changes over time and you don't know what it is, and you want to even, over time, have a heterogeneous deployment of this. So it's very, very important for your implementation of your storage volumes to actually be abstracted behind a common API, which is the Swift API. So this is what Swift does. So if you're going to these fancy new optical drives that are called Millennium drives, they're supposed to last 1,000 years, no degradation. If you want to store optical data, if you want to use traditional SATA drives, if you want to go into, deploy Commodore 64s with tape storage in your Swift cluster, I guess you could do that. Fancy little graphic at the bottom talking about the hammer technology, the heat-assisted magnetic recording. Is just another way to do dense magnetic storage on spinning media. And the point is that the actual technology behind your storage is changing over time. Everything from using shingled magnetic recording, the hammer stuff, new optical drives. That other little picture up in the top there is a picture, I think, off of HP's website or something about memristors. The point is things are changing, and what you really want is to be able to have this abstracted, and you want to be able to have a different implementation for the actual storage volume. So here's where I'm getting into it, an actual very practical example of something that has been recently demonstrated as working inside of Swift. And then I'll kind of tie this together with where we came from. So in Hong Kong, at the OpenStack Design Summit, we demoed and had a lot of actual display units to people to pick up and look at. Seagate's new technology, which is called kinetic drive, which is a network-attached drive, does not have a block interface. It has an Ethernet interface and uses a key-value API. So you don't talk to it with a, you don't put a file system on it. You just say, hey, here's a block, here's a key, put this value on it, and then the firmware for the drive itself is actually figuring out the on-disk layout and things like that. The point is on these sort of things is that it's radically different, and you need to still be able to talk to, in a heterogeneous way, in a single cluster. You need to have SATA drives, you need to be able to have your kinetic drives, you need to be able to use other sort of implementations of this. And so I definitely want Swift to be known as, and I wanted to take the opportunity to say that absolutely, Swift is a highly extensible, pluggable system which allows you to bring in alternate vendor implementations of a storage technology and do that yourself, so that you can, just as you bring in different hypervisors, just as you bring in different network providers for other OpenStack projects. Within the OpenStack Object Storage project, you can bring in and abstract away different vendor implementations. It also happens that the out-of-the-box open source implementation that is included with Swift is extremely good, and most people are doing that. Now, there has been some recent work, which is I'm going to kind of dive back into the normal flow of this presentation, that has made that actually a lot easier as a result of some of the things that Red Hat is doing to make sure that when somebody is speaking object storage to their Gluster systems, they're actually using upstream Swift code so that you've got this abstracted out, heterogeneous, pluggable storage system. So I hope I did that little thing justice in just a few minutes. So I'm sorry I went so fast there, but it's something that keeps coming up, and I wanted to take the opportunity to say, stop. Because it's not true. Let's go on, and it will actually touch back onto the idea of this this idea of pluggability and things like that as we get into what erasure codes and then how storage policies work within Swift and this ongoing work. So back into the normal flow of conversation, the original thing I was saying, okay, Michael, I want to talk about erasure codes and storage policies. So the first question that always has to start with any kind of new feature that you're adding into any sort of system is, why in the world are we doing this? Our fingers aren't tired of typing, so there's got to be something else than just I wanted to keep my fingers warm by typing some more. So the really cool thing is let me back up just a little bit. Remember back when this whole virtualization started. I'm going to take my compute instances and I'm going to start virtualizing them. So when this started, between 10 or 20 years ago, the idea really came in, well, the main reason that people would deploy this is because they said, you know what, I don't want to buy as much hardware. I don't want to spend as much money on actual hardware. So the companies looked at it and said, my devs keep asking for more and more and more servers. I wish they would stop that. Servers are expensive. And they said, I know, I'm going to use virtualized servers, and I can put a lot of them on the same amount of hardware, and I can pass them out like candy, and it's going to be great. So the overall design, or the drive behind the initial growth of virtualized compute was saying that I don't want to spend as much money on hardware, and I'm going to make better use of the hardware that I do have. I'm going to come back and finish that in just a second. But the same concern happens today with storage. You look at a system and you say, you know what? Storage is expensive. I'm spending a lot of money on hard drives. I wish I didn't have to spend that much money. So it turns out there's been for a long, long time, about 50 years, a technology that has been researched called erasure codes. And it turns out that they promise to let you solve this problem. I want to have the same amount of durability for my data, but I don't want to spend as much money on hardware. So what are erasure codes? The thing is, every single one of us in here have used erasure codes. And the reason I know this is because they're implemented in a version of erasure codes are implemented in RAID 5 and 6 volumes. We've probably all taken advantage of RAID volumes. If not, have you ever used a DVD or a BluRay? It turns out that the encoding on that is actually a basic Reed-Solomon erasure code. The point is, you've got this ability to take your data, break it up into a bunch of chunks, do some math, add in some new chunks, and then save all of those chunks in different places. And now you're able to have very high durability without as much overhead. So let's compare this, and then I'll get into some more specific numbers on that. So comparing replication, which is how Swift works today, with erasure codes. So to start with, if I've got a 3x replication, which is generally a pretty good balance between cost and reliability, you've got a 300% overhead in your storage space. If I want to store 1 gigabyte of data, I've got to have 3 gigabytes of data available to store it 3 times. Makes pretty good sense. Erasure codes promise that, you know what, I can actually get a lot better than that. Maybe I can get as low as, maybe just 140% overhead or something even less. The thing is, though, with replication, I've got 3 copies, so I've only got 3 servers that I've got to deal with and 3 locations of where I'm storing the data. So that's pretty nice. It's a pretty low number of connections, especially when you get to erasure codes. If you've got 14 different chunks that I've got to store that same amount of data, then I've got to talk to 14 different hard drives at least, and probably more like 14 different servers, which is just a lot more network connections and TCP overhead and things like that. Replication, it's incredibly simple. Store data, store data, store data. It's pretty easy. It's very, very low CPU intensive. Erasure codes, remember that you do math step? Well, that math is expensive for CPUs. So you have to significantly increase your provisioned CPU per unit of storage. Replication also has the advantage of, I need to go grab some data. Well, I can get it back immediately. As soon as that time to first byte latency is going to actually be pretty low. And your overall throughput could be higher because all you're doing is streaming it off of a single spindle or a single SSD or something like that over the network. And it's a pretty simple system that it's easy to accelerate. Erasure codes, however, is that you may be pulling a chunk that you've got to do that math on the other side to rebuild it so you can pull it back out. And that just means that you're going to have more CPU time, the higher number of network connections, which means that your time to first byte may be lower because anyway. Point being here is you've got one particular coding mechanism is not good for every use case. You've got replication, which is really good for certain use cases, especially those kind of use cases where you need to have low time to first byte, you need the simplicity of things, or you need something that's specifically with smaller content. Erasure codes, however, become much better when you've got these larger sets of data, multi megabytes to gigabytes of data in one logical object that you're wanting to tie together. And so that leads us to a couple of things that we're looking at as far as a target use case for erasure codes. First, we want to make sure that clients are understanding their data. They know what their data lifecycle and workflows are going to be. Let's not try to solve that for them at this point. That's a hard problem. Another thing you're wanting to know is that, or another feature of this target use case is that the client is going to understand the differences in those replications. You're not going to store all of your 1K cat photos with erasure codes. However, it turns out that erasure codes may be a really good thing for storing backups or VM images for all of your data, because those are large and those are going to be relatively low read rather than the much more high throughput on, say, direct accessible web content. And so the other thing we have to look at is that we're adding this capability into Swift, so we can't just say, guess what, all new clusters get to use erasure codes, but all of those public service providers like Rackspace and HP and IBM and all those private cloud people who have deployed Swift, sorry, you can't actually do that unless you go buy a new cluster. That's just not going to happen. So we have to have a nice migration path. So how are we going to do it? I'm going to rush through this part very, very quickly because I took my detour earlier, and then we're going to get into storage policies and tie it up. So high level, what are we going to do? We are going to make sure that the erasure code happens in the proxy server. Because guess what? People who are deploying Swift now are already optimizing their SKUs on what they buy, their proxy servers, for CPU. They're optimizing their storage nodes for IOPS and dense storage, $ per gigabyte, things like that. So that kind of keeps that CPU cost in the same place, which is nice. Also, that we want to be able to specifically say what content is marked as erasure coded versus what is not. And so the way we're going to do this is that we're going to have a granularity on a per container basis. So in Swift, just as you can say this is a versioned container, or this container over here has a particular set of ACLs, we're going to be able to say that this container is going to be erasure coded. I'm going to store things into my backups container, therefore the objects inside of it are going to be erasure coded. A nice thing about this is that flag there is actually, it's a grouping for a large number of objects, and it's already very, very highly cacheable and cached inside of Swift, inside of the normal data flow. So that's good. So that means that we've got, that gives us the target of what we need to work on. So this is a current work in progress as far as what we need to do. We need to we need to make sure that the proxy server can understand this is erasure coded data versus this is not, and needs to be able to know when to call those erasure coded libraries and know how to get all the hooks the right place. We also need to make sure that we've got a process to resolve some edge cases on what happens if I tried to create a container one way and then I tried to create it someplace else, and we've got this conflicting, is this an erasure coded container or a replicated container? So we've got to figure out a way to do this. We've got to be able to, let's see, which way are we going here? We've got to work on a way to do the rebuilding and checking of those erasure coded chunks instead of the simple replication process that we have today. We've got to be able to make sure that we can rebuild these erasure coded pieces. Another question that comes up is, which erasure coded scheme are you using? And the idea here is use what's available in the library you're using and let that library be pluggable with a constant interface so that you can use an upstream open source erasure coded library, which is actually we've got some people working on right now. But you could also, for example, use a proprietary one or a non-open one at least that is provided by, for example, Intel that's optimized for their particular chipsets. So that's kind of an interesting thing. So the idea is to still provide flexibility on what sort of erasure codes are supported. The on-disk impact is going to be pretty important because you need to be able to know, you need to be able to segregate the data on disk. So this is where it starts to get pretty interesting. If you remember, we had that on-disk layout earlier, and I didn't highlight it, I should have. We had all of the data was stored in this objects directory, kind of top-level thing, and then we had some hex letters after that. But it was all stored inside of this objects directory. So the idea here is let's not re-provision that, but let's use a separate sibling directory. Let's call it EC objects or something like this. I'll get into what that something like this is in just a second. And let's store all of the erasure-coded chunks in that directory. What that allows you to do is to very easily segregate out your replication processes from your erasure code rebuild processes and things like that. So let me skip over a few of these things. Well, let me go over the put and read, the read and write, the write and read cycles very, very quickly, so we get kind of a good picture of what this is going to do. So first, client's going to upload data. So the proxy is going to receive the data, and what it does today is it reads a chunk of data off of the network, and then it streams that in triplicates out to the back-end servers for 3 replicates. So with erasure codes, it's going to do something very similar. So let's suppose you're using an erasure code scheme that's 10 primary chunks plus 4 parity chunks. So you've got 14 total chunks that you're going to be doing. That means you're going to be talking to 14 separate storage volumes. Point being is that the chunk comes in, the client request comes in, and then the proxy server gets that chunk of data, erasure codes it into those 14 different pieces, puts those out to those servers. Next chunk of data comes in, puts it out to the same 14 servers. So what you end up with is you end up with something on disk which is really like a lot of different stripes. You've got this striated piece of data on disk, which is first chunk. Let's say you're on server number 1 out of 14. You've got your server number 1 chunk, and then you've got basically chunk, the stripe 2 chunk 1, stripe 3 chunk 1, and things like this. So you end up with 14 files on disk. Yes?
You've got quorum chunks there. Is that the same as exactly the amount of data that's uploaded?
You got this word, yes. Okay, quorum. So that's another consideration that I kind of glossed over a little bit. But thank you for bringing that up. So right now, quorum in Swift is a majority plus 1. With 3 replicas, this means that you have a quorum size of 2. So if you write something out to Swift today, if 2 drives successfully flush it to disk reliably, then the proxy server can return a success to the client, regardless of what happened to the 3rd copy, because replication is going to take care of that. So in other words, you can actually survive. You can survive some good durability things there. But the quorum in erasure codes is the same sort of things. You want you want to be protected from more than just a single drive failing, which if quorum size was 1 and you lost 1 drive, well, you completely lost your data. That's bad. So basically, it's how many data loss plus 1 drive is quorum size with 3 replicas. With erasure codes, it's going to be very similar. It's basically going to be what is the number of parity chunks plus 1. So if you've got a 10 plus 4 scheme, you've got a quorum size of 11. Because you need 11 chunks, which means you can survive the loss of 3 in order to still successfully be able to rebuild that data. And you want to be able to withstand some other failures so that works. So the read request cycle here is that the request is going to come in, the proxy is going to determine, yes, that it was for erasure-coded data. Now I need to go look this up in the particular erasure code placement, the ring there, feed those chunks back, and we can either just look for just the primary bits, or we can just get, say, a quorum number of them, or we could try from all 14 of them and all of the chunks, and stream the system back. The nice thing about this is that you can still continue the stream even if one of those chunks dies, because you can still mathematically calculate what that chunk would have been. It's kind of one of the advantages of erasure codes. So that's kind of how that flow works. So I'm going to skip over deletes because it's pretty simple. Let's see, we're going to audit the chunks just as we do now. Keep the checksum of each chunk, therefore the auditor doesn't really have to change. The EC reconstructor will be the replacement of the replicator now. It's kind of a check your siblings basis, so you don't have this n-squared explosion of connections. In other words, if you've got 4 chunks there, chunk 1 can check for chunk 4 and chunk 2, kind of in a loop there. But if chunk 2 is missing, then chunks 1 and 3 will detect that and can start rebuilding and figure out how that works. There's a couple other things we need to worry about on the placement there. And in the interest of time, I'm going to go on and talk about where the things that are really interesting about this. So remember the analogy that I started with earlier about the server virtualization. People started embracing server virtualization because they wanted to make better use of their hardware. It's the same impetus that people are looking for, erasure codes are looking for. They want to make better use of their hardware. They don't want to have that overhead of using a lot of drives to store a little bit of data. They want to be able to store more data in that same number of drives. Well, the really cool thing that happened with server virtualization that basically gets us all into this room today is the fact that server virtualization became much, much more than just making better effective use of hardware. It suddenly allowed companies to very flexibly and very precisely adjust their compute needs for their use case, which is a really, really powerful thing. It means that you can go up and you can scale up and down very easily. You can make use of downtime. You can smooth out your spikes. It's just a huge amount of flexibility that, like I said, gets us all into this room on the OpenStack mini-conf today. So the really cool thing about erasure codes is that we get the same advantages because in order to implement erasure codes, what we have to do inside of Swift is implement an arbitrary storage policy. So what is a storage policy, you ask? I'm glad you asked. A storage policy is made up of 3 things. A storage policy is the combination of what hardware are you running on, how are you storing your data across that subset of hardware, and then when you actually get down to talking to that storage volume, how are you actually talking to it? This is kind of that pluggability thing that I was coming back to later. This is some things that have really been made much cleaner. It's always existed in Swift, but it's been made much cleaner recently with the work that Red Hat has been doing to run Swift on top of Gluster volumes. So those other 2 things. We've got a globally distributed Swift cluster. If you want to know how that works, come to my talk later this week. We've got a globally distributed Swift cluster. Now I need to choose what subset of hardware I'm going to store my data on. That may be I'm going to store it replicated across the entire world. It may be that I want to store it in the east coast of the US. It may be that I want to store something in the EU, maybe something I want to store in Singapore or something like this. The point is I can choose now what is the geography. Or maybe instead of choosing geography, the subset of hardware is based on SLA. Maybe you want to say this is going to be my SSD and this is going to be my SATA stuff. And you can offer different SLAs for the same amount of data. Once you have the hardware that you're choosing, then you're actually able to choose how do we store this on that hardware. So in order to be able to support erasure-coded data, we also need to be able to support an arbitrary number of different types of ways to encode it, which could be other replicated schemes. Perhaps you want to support reduced redundancy because you just need to store some thumbnails that you can recreate, but it sure is nice to keep them around. Maybe you want to store something that has a very high replication scheme because you want to store a single copy in your 6 data centers around the world. Or maybe it's something that you've got different erasure-coded policies that you need to do based on different cost-benefit of the different advantages of different schemes, different parameters, things like that. So then you've got the combination of these 3 things, which becomes extremely interesting. You can just imagine that now you've got your geography multiplied times the options of SLAs, multiplied times the options of different ways to store the data, and now you've got this combinatorial explosion of possibility as far as how do you store your data within a Swift cluster. And you can still manage it inside of the same object storage system. So this is really cool. In fact, I would dare say it's pretty huge, or it's huge. To me, this is the most exciting thing and the biggest thing to happen in Swift since actually it was open sourced. So up to this point, all Swift clusters basically have one storage policy. Your data is replicated. And you could change how many times it was replicated, but that was a per cluster setting. What you're going to be able to do now is choose how do you store different types of data and very specifically tailor your storage needs to your use case so that you can say, I've got backups, and I've got web content, and I've got this other stuff over here, and I've got this regional office over there, and now I can manage one logical Swift cluster and be able to do this. So, it's all well and good. Show me the code. Well, it's a work in progress, but you can still go look at it. It has not yet, there's parts of it have been merged into Swift and released, including the disk file abstractions and the ability to clean up how things are talking to the particular storage volume implementation. But there's other work right now that's working on getting all the multi-ring stuff working. And the progress that we're going here right now is we're working on a separate feature branch through Garrett, through the OpenStack processes, and we are making sure that you can have multiple Swift, multiple replicated rings to start with, and that is all working. That's great. I'm actually just about to demo that. And then we've got, the next steps are going to be making sure that there's a migration path that we have to work on, and then there's some of the back-end processes as far as making sure replication and stuff like that works. That's going to be able to be merged into master, and that should, I'm very confident. In fact, we've got a little sprint on it next week in the Bay Area. I am very confident that this is going to be easily merged into Swift in the Icehouse cycle, development cycle for OpenStack. Once we have those things done, once we have the foundation work done, that's when we're going to be able to add on erasure codes. As soon as that's done, we're working very closely with both Intel, Box, and Red Hat to make sure that this is working. We've got a gentleman named Kevin from Box who is very, very good at erasure codes, working on some libraries there that are open, Python bindings, so we can easily use this. Great. So now the fun part, demo time. Michael, how much time do I have for a demo?
You have 13 minutes.
13 minutes, that is perfect. Thank you. There we go. And, okay. Let's clear that out again. Oh, sorry. Clear. Okay. So I've got my Swift all-in-one over here running. I've got I'm on the erasure code branch of my Swift cluster and of the code checkout. And I have on my Swift all-in-one, I am running a watch command so you can see the .data files. So if you remember, the path that actually looks like on disk today is you've got a prefix, which in this case is, well, I'll show you. So in here we've got the mount points for the actual, you can see at the bottom here, the mount points for the drives that I'm using. And then inside of there, you've got a few different levels of directory, but it ends up storing on disk with the .data file. That's where your data is actually stored. So the other thing that's very interesting here is, sorry, let's do presentation profile. In my Swift config file, swift.conf, I have a couple of storage policies defined. I have policy chicken and policy turkey. And I specifically chose those names because they mean nothing. There's not like you have to say, this is going to be reduced redundancy, this is going to be something else. So the point is, you see that I've got a couple of config sections here, storage policy 0, storage policy 1, storage policy 0 is part of the migration story. That is a special number in that by default, if you don't have any storage policies defined, it's storage policy 0. This means that also you can migrate from existing clusters and everything automatically gets storage policy 0. So let me just show you what happens, then we can talk about what did happen. So I've got I'm going to get an auth token. Come on, typing. OK, so I got my auth token, and I made a little request to the auth. Now let's create a container there. Create my container, and I'm going to create an object inside of it called O. And my data is going to be the bytes 1, 2, 3, 4. Fantastic. 201 created, everything is good. Now, what happens? Well, you'll see there that I have a few interesting things. One is I've only got 2 copies of this. Well, it turns out that if you look back at my data, I'm going to do a read on this data. Where is it? Ah, it's because I didn't set it. It's OK. So I set this policy as, let's see, Turkey policy as the default policy. So all new data that was not specifically created in a container that had storage policies set, this is what I wanted to see. Let's do a git on the object server. And you'll see that, I'm sorry, the container itself, x storage policy index 1. The reason is because I have this default yes. So anything that wasn't specifically set when I created that container, it was set at the storage policy 1. So I've got my Turkey policy here. And if you looked at what's inside of my Swift directory, you'll see that I've got a couple of different object rings. I've got object ring, but I've also got object-1 ring. So object ring is for my storage policy 0, object-1 is storage policy 1. So that's where I chose that I set that up with a 2-replica cluster. So you can see now I have 2 data files. They're inside of the objects1 directory, and then you've got a couple of the displaying functionality to spread it out on disk. Just to show the rest of that, if I look at, what is that? Storage policy files, and I look at my remake rings, you can see that I'm creating a storage policy 1 with simply 2 replicas, and I've got my storage policy 0 I'm creating with 3 replicas. So I ran this, and then I copied it out into the right places with an object ring and then an objects-1 ring. Now the cool thing is, I've got 4 drives set up, but I've only got 2 replicas things here. So let's create another container. Let's call it C2. I'm going to still create that container, but this time I'm going to say that it is X storage policy chicken. Fantastic, it was created. So let's see what that looks like. Now I get this back, and I see that it's X storage policy index 0. So let's create another object inside of there. Same object name, same object content. I'm going to use it in C2, though. Got that data back, and you'll see that on disk, I now have more data. So you'll see that I've got 2 of them in objects-1. That was my first set of data. And I've got 3 of them in objects-2. That was my fully replicated set. So I was still able to use all of my drives effectively, but now I have 2 separate storage policies living side by side. And that is what's really cool about storage policies. So with that being said, in the minutes we have left, that was a lot of data really fast. So thanks for paying attention. What questions do you have? Michael.
So I went and had a look at the kinetic driver, because I totally didn't realize it existed.
Yeah.
It's not in the tree at the moment, right? It's separate. Is there a plan to merge them?
There is not a current plan to have the kinetic drive, as you would phrase it in the Nova world, the kinetic driver merged into the upstream trunk at this point. For other reasons, it's not yet publicly for sale, and the functionality isn't completely done. I mean, it's a very nice proof of concept demo. We can show that it works, but it's not production ready, let's say, either on the hardware or the software piece. But the code is completely open. If you wanted to see that code, you can look at it right now. It's on GitHub in the Swiftstack repository, and see that there. What other questions? I covered a lot. Erasure codes, storage policies, pluggability of Swift.
Although your demonstration is on a single server, is that true that Swift is primarily used for the cluster type infrastructure?
Yes. So the question is, I should have said Michael's question for the view. The question was, where's the code for the kinetic stuff? The code you can find is on the Swiftstack GitHub page. So the question is, my demo was on a single server. Yes, it's running on a single VM in VirtualBox. But Swift is designed and primarily used in a clustered sense. So what I would say about that is, My server here is actually running 4 copies of everything to simulate multiple servers, and it has 4 drives, one server associated with all of that. Yes, this works in a server setup so that you can run this throughout an entire cluster.
Yeah, the reason why I asked this question is my organization is still using file-based storage. We have a huge petabytes.
Mm-hmm.
We have files typically of 5 gigabytes or 10 gigabytes.
Sure.
Usually installed in the paper packed
Mm-hmm.
file system.
Okay.
So people think about using object store. I mean, if Swift is primarily used for a cluster, you have to maybe clusters
Yes.
as a storage, then partition big file into smaller chunks.
So,
So that case of use scenario, how do you?
well, for the video, to sum up what you were saying is you've got lots and lots of data, petabytes plus of data in file systems, giant filers, some of it even on tape. So if you're interested, yes, you should definitely consider object storage. Good idea. Swift is a really good way. Yes. So I've seen lots of people who have migrated from filer-based storage into Swift successfully. One of the things I wanted to point out that you would probably be very interested in, we have a current patch outstanding right now. Wasn't appropriate to talk about here, but it's a really cool thing, which is a migration container sort of functionality so that you can say, here's a container and it actually mirrors my filer over there. And if I request data from Swift and it's not in Swift, then it'll fetch it from the filer, store it in Swift, and give it back to you. So the next time you ask for it, it's already in Swift. So it gives you a nice lazy loading of migration from that. So yes, that is an active problem that we are currently working on upstream in the open source community. It's stuff that we work on at Swiftstack for our customers and things like that. You had a question here.
I was just going to say, I presume if all of the data blocks are available, you won't put everything strapped on the read, so the reads will be just as cheap as what you've done with it?
It's not going to be just as cheap because you still have the additional TCP overhead for the additional servers, right? So the question is, if you've got all of the chunks available in erasure-coded storage, you wouldn't necessarily need to try to connect to all of the servers and do the reconstruction on the way out. Yes, that is true. You do have the additional TCP overhead for that, which is probably going to be washed away in the actual transport time because you're going to be storing large data sets in EC data. But that being said, it hasn't been written yet, that particular part of it. So I think that that's a very strong argument on one side of it. The other argument on the other side is saying that you can easily fail over if you lose a chunk during the read, which may be more likely with larger data sets. If you're downloading 5 petabytes or gigabytes of data at once, or even more. So, Florian?
Can I ask a question that's related to Swift but not related to what you said in the talk?
Absolutely.
Okay. What are your current best practices that you would recommend for people who want to use Swift global clusters for client's image storage?
Yes.
And make sure that they correctly replicate client's metadata between sites?
I think that it's probably a longer answer than we have time for. I will also, of course, plug my cluster talk on global clusters that's going to be on Thursday. The basic idea, well, Swift is not solving your metadata storage in glance problem. And however you're going to replicate that, that's going to be the responsibility of the deployer / glance to make sure that those work and are synchronized and things like that. There's basically a couple of considerations you have with global clusters data. One is, are you trying to make sure you have a copy everywhere, or at least one copy everywhere? So that's the question is, I've got 5 sites. Do I need to have 5 replicas to make sure they're everywhere? But that's 500% storage. Or am I okay with still full durability and it's in 3 of those sites? I'm just not entirely sure which 3. You can see how global clusters plus the storage policies is going to be a really, really great thing. But that's the question you would have today as far as, let's just suppose I've got a New York location and a London location at that point, and I need to make sure I have data in both. So if you've got 3 replicas of your data with 2 locations, you can be guaranteed you have at least 1 replica in each of them, and you can route between those with whatever DNS solution you need to do that. Swift supports, with global clusters, the ability to have affinity reads, which means that if you talk to the New York location, you'll get the New York replica rather than the London replica. And then being able to coordinate that with the appropriate glance metadata. I have not personally tried to solve that problem, but I do not see why there's anything outside of the scope of what would be done today. So, yes?
Curious, like when you're talking about the Erasure code and using, say, an unopened library or something for it, would that just put on the cluster you're using a restriction that has to all everything in that cluster? Is that right with the Erasure code?
So the question is, if you're using a non-open library for a particular aspect of the implementation, specifically around the Erasure code library, then does that put that restriction on that entire cluster? The idea is that the library will have a standard interface and standard API. And so as long as the same scheme is implemented both by the proprietary library and the open library, then the difference should probably be performance or something like that. Assuming they're able to be compiled to the same thing and that sort of stuff. So I do not suspect that it would make that hard requirement. However, the nuances of this and the specifics may supersede that. I would assume that if you're making a choice to use a proprietary solution for a particular reason, that's probably applicable to your entire cluster. My goal, and the absolute goal in the design for the feature is that there will be an open, successful, capable, good library available. So there should never be a requirement to use that unless you have over and above things that other people are able to do some extra value on. Probably one more, maybe?
Well, you're running into the break, so...
Oh, okay, yes. Last one.
Maybe by giving some examples, could you give some use cases where Swift with EC would be more appropriate or less appropriate than either the existing Swift or
Absolutely.
other storage technologies?
Absolutely. So can you give by some examples places where erasure codes would be more appropriate than replication or not? Is that sufficient? Okay. So I would say that the two places where erasure codes would be very, very good would be when you are using Swift as a backend for glance for storing images, VM images. They're generally going to be very large, and you're going to want to, it's also not something you're necessarily going to access quite a bit. Another thing would be similar to that, backups. It's something that you hope you never have to read, but you need to have always available, and you don't necessarily want to pay the overhead of that. So server backups, I think, are probably, actually, to be honest, that is the use case that first brought EC to the forefront for us. We've got to store this. It's going to literally cost us $1 million or more a month to use replication over EC. Literally, I mean, so you're looking at $12 million a year. That was a significant thing that justifies, let's actually work on this feature. So another thing is counter that to data that is going to be, an example that I love always talking about is the fact that if you go to Wikipedia and you see an image there, it's coming out of their Swift cluster that they're running. Those are images for the web that are generally going to be very small, and there's this nice power curve distribution on the access times of those, but they all have to be very available right now. And you don't want to try to go look at some obscure page and see an image that then has to be really low loading just because in the CPU time and things like that. So if you've got smaller data sets that are or smaller individual objects that are going to be needing to have the access much more frequently than, say, backups or something like that. Even if you're looking at saying, I've got streaming data, that still would probably be something you want to replicate. I've got streaming videos or something like that. They could be larger individual things, but it's something where the throughput on that and making sure you don't have jitters based on the stream based on CPU got overloaded for some reason is fairly important. So the idea really is colder data, and by colder, the images you need to archive, your archives themselves, things like that you're not accessing as frequently. Actually, the interesting point about this that I glossed over for time purposes is, and I'll talk about now, is that one of the things that comes up is, well, is Swift going to migrate? Is going to automatically migrate my data for me? So if I don't talk to it in a long time, I'm going to automatically erasure code it. And as soon as I access this erasure coded stuff, then it's going to bring it into the faster replicated tier, and everything's going to be good. No, the answer is no, we're not going to do that. The point is that the client actually knows a whole lot more about the data access patterns than the storage engine itself does. And there's nothing that would prevent you from pre-warming a cache and saying, hey, let's pull it into this other thing and something like that. And almost by definition on these, that kind of access pattern, the data is always where you don't want it. If you're not accessing it, but it's still in the replicator because it has expired, well, you don't want it there. You want it in the cold storage. If it's in the cold storage and you need to access it, well, you didn't want it there. You wanted it in the warm storage. So you as the user, as the client, or the application, knows a lot more about the data access patterns and can do that more effectively. So the point is, erasure codes become a very nice way to augment existing Swift clusters such that if you have colder data, then you can effectively store this in the same cluster. And I can imagine public cloud providers offering this and saying, we're going to, HP or Rackspace could say, we've got our Swift cluster stored there. Now, if you're going to do snapshots from your servers, then you can put those into your EC container. Or potentially, they can make this available for other backups and charge different rates for them, or add in an SSD replicated tier and do this kind of thing. So I think, yeah. Great. Thank you very much. I'll be around all week. It's good to see you. So, thanks.